Hi class, welcome back to Electromagnetics. This lecture, we're going to continue our look at Maxwell's equations in integral form by introducing Ampere's law. So first we're going to look at a historical background, and you might be able to guess this one just based on our last lecture. But his education for this person was a Royal Institute in the United Kingdom. As far as work goes, he was considered an English commoner and worked as a lab assistant. So this is a consequence, I guess, from the class system in England. Here's a picture of this individual, and if you haven't guessed by now, this is Michael Faraday. So he lived from 1791 to 1867. So some notable things about Mr. Faraday. Through experimentation, he was able to characterize much of the modern knowledge of electromagnetic induction. So this can't be overstated that he was just masterful in the lab. He conducted many experiments and discovered many relationships, and so he had an incredible reputation for his ability in the lab and create these experiments that helped people find out things. So because of this, the first Maxwell equation was named in his honor, especially since he was a major contributor to that. One interesting fact was that Einstein kept a picture of Faraday on his study wall along with Newton and Maxwell. To Einstein, these three guys were fundamental in forming, the modern theory of a lot in physics, especially with electromagnetics. So that speaks pretty highly of him. One story that I've heard about him was that, even though he was incredibly talented in the lab and contributed to much at the universities, because of his commoner class, when they went to lecture at other places, the only way that they could get the colleges to agree to pay for his way is if he acted as like the chauffeur to drive them there or something like that. So it really just shows kind of the sad state of affairs back then as far as the class system. So we're continuing in part two. Did Faraday's law last lecture, so this time we will be introducing Ampere's law in integral form. So around 1806, a gentleman by the name of Hans Christian Oersted conducted an experiment that showed that electric currents generate magnetic fields. So this was a pretty major discovery. This was later characterized by André-Marie Ampere in 1826, and he actually really kind of fleshed this out and formulated that. So a little later, this was further shown that time-varying electric fields give rise to magnetic fields. So not just current itself, but if they're time-varying, this is where they are related. So this later led to the prediction of electromagnetic wave propagation before it was actually fully discovered and characterized by Maxwell. So Ampere's law is analogous or very similar to Faraday's law, at least especially mathematically the way it works. And so this law is expressed with this equation right here. So we're going to want to break this down, and we're actually going to introduce some new terms. But let's just give a graphical of what's going on here. So it's much like the image that we had for Faraday's law. We have this closed contour or closed path C that we had before, and this is the boundary for this surface S. And again, it's like the blowing a bubble again, and so it can be any surface you want as long as we maintain this surface vector that's always normal everywhere on the surface itself. And so what we're saying on the left hand side here then is we'll generate a magnetic field density divided by this mu naught factor around this closed circle for the summation across the surface of any current flows, what we'll find out this is, and displacement. So we're going to dig into this a little bit more. So again, starting back with this basic form of the equation, the integral of the volume current density J over S is the total current flow. So this new term J is known as the current density vector, and so when we say that, it's going to be amperes per meter squared, so it's over an area. So that's why if we multiply or dot this, the meter squared will cancel out, and that'll give us current in amps. And so that's why we can think of this integral as the current flowing, or the amperes, across that surface. The second term we need to talk about a little bit. This term on the right is the flux of the vector field epsilon naught E, so that's the electric field vector, and then the permittivity crossing the surface S. So the vector E, or epsilon naught E, this is known as the displacement vector, or maybe more thoroughly, the displacement flux density vector. And so we can replace this permittivity, free space, and electric field vector with a new term, D, or new symbol D. And so this D we'll refer to it as the displacement flux density vector. So the time derivative of the sum of this vector is associated with what we call a displacement current. So that being the case, if we look at this right-hand side, what we really have is, some people refer to this as the total current on the surface, or going through the surface of the enclosed surface that we had, S. So this is the real current, or the actual current, and over here this is known as the displacement current. So the displacement current is not a physical current or flow of charge, but it's the mathematical equivalent to current. So maybe a little hard to wrap your head around. We'll look at an example in a minute that kind of puts some real life meaning to what this term means. So if we continue on with this is our original equation. The line integral on the left side then is summing this term, which is the magnetic flux density divided by the permeability around the closed path. And again, that permeability is a function of the medium that we're working in. So if we integrate that around this closed path, that's what we're doing on the left-hand side. So this is analogous to the same integral involving the electric field in Faraday's law. We noted how this was related to the physical meaning of work per unit charge. This is not necessarily the case with the integral of the magnetic field, as it's perpendicular to the direction of the movement of the test charge. So the E field moves in the same direction. The magnetic field is related by the perpendicular. So defining new terms again here, this vector that we're integrating, this is known as the magnetic field intensity vector. And so we can denote this now by the symbol H. So B is the magnetic flux density, H is the magnetic field intensity vector. So just as the E field, as with the E field, the integral of this vector around the closed path C is known as the magnetomotive force, or MMF, whereas when we did the E field, that was the electromotive force, or EMF. So now our original expression for Ampere's law was this. This is what we started with, but we can now rewrite this in terms of these new values or variables that we define, these new vectors. And so this cleans things up just a bit. And so if we were to read this one out, we would say that the magnetomotive force on this side, which is the the sum of the magnetic field intensity around a given loop, derived vectorially. This would be equal to the total current going through a surface and the time derivative of the displacement current on the surface of our surface S. So now that we have this new form of the equation with our new derived variables, we can think of this then, like I said, in plain English, that the magnetomotive force around C is equal to the total current. Remember, we call this the total current, the actual current and the displaced current bounded by this C going through or on this surface S. And so if we look back at our original diagram, again, we have this C value here, and then we have this surface, so any current going through it or displacement current associated with the surface is accounted for over here, and that contributes to this magnetic field intensity on this circle. Suppose we have, an infinitely long, thin, straight wire situated on the z-axis. So you see that here in this image. And then it's carrying this current I. So got this wire going down the z-axis, goes off at infinity in both directions, carrying this current I. So now it's desired that we want to find the total magnetic field intensity, which that's H, around a circle of radius A, lying in the xy plane. So that's this circle here. So that has a radius of A. So we know from Ampere's law, which we just learned, that the total magnetic field intensity around this closed contour C must equal to the total current traveling through any surface bounded by C. So you can see we could define multiple surfaces here. We could use this surface, or just the flat surface in the middle. So again, it's just at any point, if you were blowing the bubble, you could stop it at any point in time, and the current flowing through any of those surfaces it should give us the same result. And so this is what the Ampere's law simplified for this condition tells us, that this sum of this magnetic field around this C is going to equal to I, the total current flowing through it. So since the wire is infinite, again, it doesn't matter which of the infinitely many surfaces we choose, the current I will have to pass through all of them since the wire is infinitely long. So this being the case, we can now divide this closed contour C into a finite number of segments N. So that's what we're doing here. So remember, it has a radius of A. We're cutting it up into N pi slices, if you want to think of it that way. And so this being the case, we can now define H for each segment on here, each separate segment, as follows. So this H dot dl, so you see we'll have the H and the L's in the direction of the circle. This is going to be equal to 2 pi a, which that's your circumference, right? 2 pi a, 2 pi r, but a is equal to r is equal to a, divided by the number of slices, and this will be multiplied, that's our dl term right there, and that'll be multiplied times h. So if we sum up the h values for each segment, this will give us an expression for the left-hand side of Ampere's equation as follows. So we have got this, again, this left-hand side of Ampere's law. So we take our 2 pi a over n, which is our dl term, and we have our h, which that's just the value of our magnetic field, and we're going to multiply that times the total number of segments, which is n. So we put it over here. So you can see that the n's should cross out, and so, or cancel out, so that would leave us with 2 pi AH for our total magnetic field intensity around that curve, circle. So according to Ampere's law, we remember that that's got to equal to the total current flowing through there, and we've already said the only current we have is on the z-axis, infinitely long wire. So that being the case, we can say then that this magnetic field intensity is equal to I, or the total current, divided by the circumference of the enclosed circle. So what about if we don't have an infinitely long wire? So now let's take this into consideration, the case where the wire is not infinite but finite. So this means that not all surfaces are penetrated by the wire or the current I. Now, don't ask me exactly how you do this, but for this special case, kind of a thought exercise, we're going to do this. So in this case, we must also consider the displacement current as well. So before we only had to worry about the actual current. Now we've got to take into account displacement current. So this being the case, the total current, both conducting and displaced, must be equal for all surfaces. So depending on what surface, you take this S1, which is the flat, part of the circle, or you got this S2, or you got this S3. Doesn't matter which. If we add them, the actual or the conducting and displaced current on this surface, then this surface and this surface, they must be equal. So let's consider a couple of these surfaces, S1 and S3. If we do that, then the sum of all the actual current and the displaced current on S1 has got to equal the actual current and displaced current on S3. So we know from before that for surfaces S1 and S2, we have that the summation of the current density times the surface area is going to equal to the total current flow. And for S3, where it doesn't penetrate, we know that this has to equal to 0, right? Because there's no current flowing through that. So if we substitute this back into our original equation, we should have this right here. So the sum of the currents on S1, both conducting and displaced, has got to equal the sum of the conducting and displaced current on S3. So what this means then is we know that this is equal to I, so we replace it with that, and then we know that this one there is no current flow because it doesn't penetrate that surface, so that gives us our 0 here. So if we rearrange this, what we come up with then is that the total displacement current of S3 minus the displacement current on S1 has to equal to the total current going through the surface S1. Or we could say that the total displacement current of surfaces 3 and 1 has got to equal to the total current. So this might help us understand a little bit more what's actually going on with the capacitors. I know for some of the younger students, they have a hard time accepting that, okay, there's no physical connection across this for the capacitor, it's just these plates. Well, what's happening here then is we have this conducting current coming all the way here. So if we were to draw this surface S1, we have the conducting current. But if we were to draw the same circle with this second surface that goes through the middle, well, you don't have conducting current going through it, but now you have displacement current. So that's what actually is going on inside a capacitor is the current's being displaced, and so that's why it appears once you get to the other side, if we were to draw this surface back around here, you're going to have conducting current back on the other side. So let's look at some examples. We want to now consider a time-varying field defined by this equation. So it's a sinusoidal field, and it's in the x direction. So we have this electric field, and so it's denoted by the x's. Then we also have this loop going around here in the y and z, and their distances are b and d for all the sides. So we want to ask the question, what is the MMF, or the magnetomotive force, induced around the loop given below? So in this case, all of the current is displacement current here, right? So when we look at that, then we can take this equation then for any surface that we want to define. We're going to take the surface of the area of the rectangle, and so we're going z goes from 0 to b, and y goes from 0 to d, and we're going to integrate our original E field. But remember, to get from an E field to a D field, we have to multiply by this permittivity, because that's how we defined D in the first place. It was the permittivity times the E field. Of course, this is in the x direction. Our area vector is also in the x direction, so this dot product of these two unit vectors will be 1. The sinusoid is not dependent on z or y, so we can pull that out. It's only dependent on t. So now we're left with the z part of this expression up here, so we will integrate that across those limits. And when we do, we come up with the permittivity times b squared d over 2 times the amplitude of the electric field times the sine of omega t. So if we want to now apply Ampere's law, remember we're looking for the MMF. We haven't got there yet. This is what's going to be on the right side of Ampere's law, or a factor in that, but the left-hand side is what we're actually looking for. So to find that, we need to take the time derivative of this guy, because there is no current flow, so this goes to 0. As we said, all the current was displacement current. So then we just substitute this in for our displacement summation, take that time derivative, which the only thing that's varying on time is the sine function. So when we do that, we now come up with the permittivity times b squared d over 2, the amplitude times the frequency times the cosine omega t. So this would be the MMF around that loop.